So hi everybody, this is an ARCHER2 virtual tutorial or webinar, and we use them to highlight computational work done on the ARCHER2 HPC system. Just my name is David Henty. I'm in charge of a lot of the training at EPCC, including our MSc program. Today's speaker is going to be Dr. David Lewis from the University of Liverpool, and he's been working and recently completed a software development project they're called ECSE projects, funded to do development work on ARCHER2, and it was done in collaboration with my colleague Mario Antonioletti here at Edinburgh. So I'm not a mathematician, but I do understand that the Hardy function plays an important role. I'm getting this in the theory of the Riemann zeta function, and the location of the zeros of the zeta function is considered by many to be one of the most important unsolved problems in pure mathematics. It's very interesting to have a talk in computational mathematics, because a lot of our talks are often in computational engineering or fluid dynamics or astrophysics or climatology. So something in pure mathematics is very interesting. So without further ado, I'll just pass over to David if you want to start your talk.
Hello everyone, good afternoon. I hope you can all hear me and see my slides. Okay, so what I'm going to talk to you about today is some new high-performance algorithms for the computation of the Hardy function. My name is Dr. David Lewis, and I've had a considerable amount of help on this project both from Mario, and I'd like to highlight the contribution of Ashley Brereton, my former PhD student. He's made an invaluable contribution to the development of this work. This project was supported under an ECSE project, the title you can see there, and I've had help from both Chris Johnson and the ARCHER2 support staff. So what I'm going to do today is tell you a little bit about the Hardy function, but in the main I'm going to focus on aspects of the computation of it. So it's a computational type talk. But I'll start off with a little bit of history. So the first couple of slides are a little bit of history, just to sort of set things in context. So the Hardy function, so a brief outline of its importance. As David said, what we call the Hardy Z function plays an important role in the theory of the Riemann zeta function, and it has a deep connection mainly to the distribution of prime numbers, but there are lots of other areas of maths and physics as well. And it basically represents the amplitude of what we call the zeta function along the critical line. The critical line is in the complex plane. It's the line with the real part a half and then the imaginary part it. So t can be a real number. And it's defined in this way. It is essentially just a real number. It's the amplitude. This phase term, this is theta t, is a real number here. So it's basically the amplitude of the zeta function along the line a half plus it. And there are many important mathematical results associated with this function. But as David said, the most famous, of course, is that the Riemann hypothesis, which is a Millennium Prize problem, states that all the non-trivial zeros of this particular function, when this is a complex function, so you imagine this just being a function of z, so all the values of z here that make this zero actually make this zero too. So there's a one-to-one correspondence between the zeros. So all the zeros actually lie on the critical line. They have a real part equal to a half. And what that means is, in simple terms, is what we call a prime counting function, pi of x, which is the number of primes less than x, satisfies something called the logarithmic integral, where you can think of that as just x divided by log x. So the number of primes less than x is x divided by log x plus a very small error term, a term at the square root of x. So in other words, this simple approximation is a very good approximation for the number of primes. The trouble is, this has never been proved. So we believe some zeros could lie off the line, in which case this error term would be much larger. And just to mention, the Hardy function is named after Godfrey Hardy, the famous Cambridge mathematician. I suppose he's most famous for writing, well, apart from his work, his technical work, he wrote the book A Mathematician's Apology, where he basically said, in part, that number theory would have no practical uses. And considering how important number theory is today in, say, encryption algorithms, that kind of thing, he was proved a little bit off the mark there. But if you're interested in his life and certainly his work, do look him up. He's a very interesting guy. Okay, so let's move on to the computation of the Hardy function. What we want to do, mathematicians obviously want to understand a great deal more about the behavior of this function z of t, and in particular where the values of t where z is equal to 0. And back in 1914, Hardy was the first to prove that actually z of t has an infinite number of zeros. So there are an infinite number of t values here that make z here equal to 0. Whilst at the same time, the spacing between the zeros and the amplitude of the corresponding local maxima and minima of z of t would be indicative of possibly a zeta 0 lying off the critical line in violation of the Riemann hypothesis. So you can study the maxima and minima and you can get indications maybe there's a 0 there that is not in the right place. In order to do that, you need a computational algorithm, and the starting point for any computational algorithm is an asymptotic formula for z of t. So we're interested in calculating z of t for large values of t. That's what we're interested in. It's easy to calculate z of t for small values of t. That's been done many, many years ago. But we're interested in what happens when t gets very large, and I mean potentially very, very large. And for many, many years, indeed up to the beginning of the sort of 21st century, the most efficient method of calculating z of t was what's called the Riemann-Siegel formula. And it basically states it's just a sum of cosines. So cosine, this is a real number, t is a real number, its logarithm is real, divided by the amplitude, square root of n, multiplied by 2, and then there's a small correction term here. And I'll emphasize n of t, the number of terms here, is proportional to the square root of t. So the key point is that this is an order t to the half operational method for calculating z. So you need to do square root of t, basic operations, cosine, square root, that kind of thing, to find z of t, find your value of z of t. And as I say, that was previously the most efficient known method up to the end of the 20th century. And why have I got a picture of Alan Turing here? Well, of course, we all know that Alan Turing was fundamental in setting out, doing his work on computational numbers and setting up ideas about the basis of mathematical computation. But it's interesting, during his career, when this formula was discovered, Turing was interested in it because he actually believed the Riemann hypothesis was false. And to do that, all you need to do is essentially do some calculations of this and actually come up and find a particular 0 that is a critical line. And he came up with, well, whilst on a visit, actually as a connection to Liverpool, whilst he was on a connection to Liverpool, he actually came across what we call a tidal prediction machine at the Bidston Observatory, which is now part of the National Oceanographic Centre. And this was essentially an analog machine for computing, adding up cosines, sines and cosines. And he realized that he could actually devise a similar type of analog machine to actually do this kind of computation for large values of t. And he even got a grant. He got a grant of £40 in 1939 to actually build this thing. And sadly, of course, World War II intervened, and he went off and did his encryption work on the Enigma machines and that kind of thing, and he never got back to it. But he did make an important contribution, something called Turing's method, which allows you to compute values of z of t and discern whether the number of zeros between two values of t, t1 and t2, is the correct one that satisfies the Riemann hypothesis. So the right number of zeros are in that particular interval. Okay, so there's a little bit of history for you. Now we're going to move on to the present day and some of the work I and my colleagues have been doing. So as I say, from the point of view of calculating z of t, the first, your starting point is initially you need an asymptotic formula. And when I say we're dealing with potential anomalies in the zeta zeros, they're likely to occur at very large values of t, certainly sort of the order when log t is 5 or t is greater than 10 to the power 70. That actually might be too small, but very large values of t like that, and a t to the half time operational method, the Riemann-Siegel formula, is not going to be much use for calculating t values that large. It'll simply take too long on any particular supercomputer that you could put your algorithm on. So we need to develop more efficient computational algorithms, and a lot of development work has gone into I did a lot of development work into coming up with a new asymptotic formula for zt, which forms the basis of the new algorithms, or the new algorithms I'm going to try and describe. So for a particular tolerance scale which the user can prescribe, and there's only two things you need in these algorithms. You need this the value of t you're interested in, and this value here which you can prescribe. You can come up with a new formula for z of t. And the first part of it you can see here looks as indeed identical to what we had before. The only difference is the number of summons has gone down with m. So m is an integer, 2, 3. And you can see if m is 2, then this is only t to the 1/3. If m is 3, then this is t to the 1/4, etc. So the number of summons is actually reduced drastically compared to what we had before, where we had t to the half. So in principle, that means it's going to be faster to compute. However, of course, what's happened to these extra summons? Well, they've been incorporated into an extra term here, which I call zp of t. And zp of t consists of 3 terms, and the first 2 terms you don't need to worry about. They're easy to calculate. They're very straightforward, rapid to calculate, so you don't need to worry particularly about these. The interesting bit is this part here, and I'm going to focus on these things I called S, Sm, and Sm minus here. These are what we call generalized Gauss sums, and I'll define those in a moment. So they are sums of length mt, or mt minus in this case. So what you do, you have essentially an amplitude term. We have a situation here where you have a sum over even integers. So alpha e is an even integer, and this interval increases with mt. So if mt gets large, the interval, there's a step size. So you jump, you don't go from 2, 4, 6, you go from 2 to 102 to 202, that kind of thing, but you can increase that interval as you go. These are just phases, so these are real numbers here. So the basic problem comes down to computing these generalized sums. And let's have a look at the definition of what a generalized sum is. So here we are, generalized Gauss sums. A generalized Gauss sum is a sum from k equals 0 to n, the exponential of 2 pi I times phi1 k1 plus phi2 k2, up to the degree of the Gauss sum, so m here, phi m k to the power m, and these are constants. These phase factors, phi1, phi2, phi3, phi m, they're all just constants. They can be determined from those even integers, so they're just fixed. So you just compute the sum. And in the formula on the previous side, this m term here, it's given by a somewhat complicated formula, but I'm going to simplify it quite easily. So here we have, let's take the case m equals 2. If m equals 2, this n value is of order t to the 1/6. Now what that means is the number of these required is of order t to the 1/3. And what you notice, 1/3 plus 1/6 is a half, and that is always maintained. So you need 1/6 plus 1/3 is a half. If you go to m equals 3, you have a quarter plus a quarter, which is a half, of course. If you go to m equals 4, you've got 3/10, 2/10, which is a half again, etc. So if you increase m, what you're doing is you're increasing the value of n, okay, and you're reducing the number of sums you need to calculate. So you start with t to the 1/3, then you go down to t to the 1/4, t to the 2/10, etc. So the crux of what I've been able to do with Ashley's help and with Mario's help is to come up with a methodology for the rapid computation of these guys. Now you would think these guys need n terms to calculate, because there's n cosines and sines to work out. So you think this is takes of order n to calculate, but that's not the case. What we've done is develop an algorithm that only uses of order log n operations for the cubic case, and to some extent for the m equals 4 quartic case too. And that's a huge saving. So if you're doing m equals 3, n, rather than doing t to the quarter operations, you're doing log t to the quarter or 1/4 log t operations, a vast reduction than computing this longhand. And that results in an overall computation for z of t of only about t to the 1/4, because if these basically log n or log t, then you only need to work out t to the 1/4 of them. So you get essentially an operational count of t to the 1/4. Remember, the Riemann-Siegel function was t to the half, so this is a drastically more efficient way of doing things than using the Riemann-Siegel formula. Okay, I hope you're still with me at the moment. Let's have a look and think a bit more about how this, explain a bit more about how I can compute this in just log n operations roughly. Now, the crucial fact is, well, let's go back. The first thing to say is we have to look at the coefficients. And the first two coefficients are quite easy. Phi1 and Phi2, they can be anything initially. So these values can be initially anything, but you can use very simple symmetry properties to move them to the range -1/2, and Phi2 can be between 0 and 1/4. So it's just symmetry operations, take off the integer part, and play around a little bit. And so it doesn't matter what Phi1 and Phi2, they can be a start initially, they can be shifted into that range. Now, the really crucial fact is in the remaining coefficients in the Gauss sums, the higher order coefficients decline asymptotically with t. So if we go back, we start with Phi3, this is much smaller than Phi1 and Phi2, very much smaller as t gets large. So in approximation, if j is 3 here, Phi3 is of order t to 1/t square root of t, Phi4 is 1/t, Phi5 is 1/t to the power 3/2. You get the idea. Each term is getting successively smaller and smaller. So as j increases, these get smaller and smaller. And that fact is crucial in what makes the particular sums that we're interested in here. So it's not a case of for general Gauss sums. It's only these Gauss sums with the asymptotically small higher order coefficients. But those are the ones that appear in the expression for Zp and hence Z. So we can then use something called the Euler-Maclaurin summation formula, standard formula, to express our original Gauss sum, which is sitting here, in terms of another Gauss sum with some different coefficients, but they're easily calculable, and a few small corrections, which I won't go into detail here. But basically, you've got your original Gauss sum in terms of a new Gauss sum. The original Gauss sum has a length Lj. The next Gauss sum has a length Lj plus 1. And when you work out Lj plus 1, it's approximately 2 Phi2 Lj. And because phi2 is between 0 and 1/4, 2 phi2 is between 0 and 1/2, which basically means you've halved the length. So then this Gauss sum has half the length here than the previous one. So you've reduced the length by at least a factor of 2. Now in isolation, that result isn't much of use, because this would still be a very large number, and even if you halved it, it's still a particularly large number. But crucially, what you can do is you can then repeat this recursively. You can take this sum, express it in terms of another Gauss sum, and halve it again, or at least halve it. Then the next one, and you can halve it again, and sometimes, quite often, you're doing much better than half, because I mean, obviously, if this is say 1/8, you're reducing it by 1/4 or that sort of thing. So this is being gradually reduced, and eventually you can carry on, and you can take your original Gauss sum of length L1 down to a vastly smaller, what I call a kernel Gauss sum of length K. And K is something, as a user of the code, you can prescribe. Actually, there's in the code, it's actually done for you, but you can actually prescribe if you're interested in doing that. And all you need to do that is, at most, J is some logarithmic of L1 divided by K over log 2 operations. Those are the number of links. So you go from your first Gauss sum to your number 2 to number 3 to number 4, all the way down to you reach your kernel sum. Then what you do is you work out your kernel sum exactly, which of course has a vastly reduced length. And then you go back up your chain, your hierarchical chain of sums, to get a value for you, the original sum that you're interested in. And round about sort of order K, you need K value to do your kernel sum, and then multiply this by this value J here. That number of operations gives you an initial estimate of the Gauss sum you wanted originally. And so that's the key to actually improving and speeding up the computation of this term ZP of t, and hence the Hardy function itself. Let's have a look at a little bit of an example of this. So I wasn't the first to come up with essentially this idea, this hierarchical idea. A previous author, Professor Harry, came up with a t to the 1/3 algorithm, which was based on using m equals 2 Gauss sums, quadratic Gauss sums. Now, quadratic Gauss sums are particularly well suited to this recursive estimation, because the recursive procedure is closed. That is, you start off with a quadratic sum, and you keep being linked to another quadratic sum. So the order of the sums is fixed throughout. So it makes it quite easy to do. The most important novelty of what the work I've been doing in consultation with Ashley is, apart from the asymptotic formula, is that you can apply this recursion procedure to more complicated sums, namely, say, cubic sums, provided one allows for the order of the sums to grow as you move down the chain. So the recursive procedure does not preserve the order. So the order does not have to be closed, provided, as we've seen, the initial high order coefficients commence at asymptotically small values. So I've got a little table here. Don't need to follow all the details, but suppose here's our first initial sum. It's of this particular length, so over 2 million. It's a cubic sum, so it has order 3. And it's got 3 parameters, phi1, phi2, and notice phi3 is very small compared with phi1 and phi2. It's asymptotically small, a very small value for phi3 compared with the phi1 and phi2, which is what we want. We proceed with a recursion procedure, so we reduce that. Is first sum in the chain, it's still of order 3. Then you go to the third sum in the chain, and this has to go up to order 4. So now it has an order, you need a phi4 parameter here. Then you go down to the fourth one in the chain, again it's of order phi4, and then you go down to the fifth one, and it's of order phi6, so you actually need 6 parameters. But these parameters can be calculated very easily from the parameters of the previous sum. It's just a simple bit of iteration procedure there. You could actually go further. You can make this smaller in this case, but there are certain reasons why you don't want to make this too small, because the small terms, you have to devote more time to computing the small terms to make sure they're accurate enough. So actually, this is a good place to stop. So then what you do is you calculate this sum exactly. So it just has 273 sums. You have a value here. And then you go through the procedure. You go back up, up, up here to the sum you want. And you get these intermediate values here, 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 here. And you come up with an estimate for your original Gauss sum compared to the exact value done if you worked it out longhand. And what you'll notice, although the absolute error increases, the relative error basically stays constant here. So it sort of jumps around a little bit and it stays fixed here. And it depends on how much time you want to devote. You can reduce these values. So there have been lots of refinements since I did this, so I can actually probably redo this and get a even better estimate now for this particular sum than I had originally. But what it does, I hope, is give you an idea of the recursion procedure that I use. You start from here, create the sums in the chain, work out the kernel sum exactly, and then go back through the chain, taking these intermediate values, and you get your estimate for the exact answer. Okay, right, let's have a think about now some runtime comparisons for computing Z of t itself. And trouble is, of course, to do actual runtime comparisons isn't very useful because people are running things on different computers and they've got essentially different processor speeds and that kind of thing. So how can I compare the various algorithms that are out there and their relative speed? So what I came up with is this idea of calculating something called a scale factor, an operational scale factor. And I take a value of t 10 to the 23. That's an arbitrary normalization value. So if you do a computation of zt at t equals 10 to the 23 and divide that, you get OFS is equal to 1. And I'm going to plot OFS here against the log scale. This is log t here. So at 23, the value is 1, okay, because it's just that. And then you do other computations for the particular algorithms you're interested in. So let's look at the blue dashed line. This is the previous best algorithm, t to the 1/3 algorithm that I just mentioned earlier. And that's the blue dashed line. So what you can see here is the curve here. So as you go up to sort of number 10, t to the power 10 to the 26, you are going to need, what's that? 12. It's going to take you 12 times as long to do compared to doing the calculation at 10 to the 23. Okay, like so. The red line shows how the runtimes would increase for a purely t to the 1/4 algorithm. So that's the red line here. So if you had a purely t to the 1/4, at 10 to the 26, it would only take possibly about 7 times to run compared to 12 or 13, so a lot faster. And then the green dots, well, these represent the results of actual runs using the new code developed for this project. So these are actual results based on actual run times, and you can sort of see that the green dots fall closely to the red line. They are much below the previous blue line, indicating how much faster the new code is compared to the previous state-of-the-art algorithm of the t to the 1/3 log t. They lie above t to the 1/4 because there's obviously this log term comes in and they sort of move away a little bit, but they remain much faster. This is spiraling upwards very quickly. This is increasing much more slowly, indicating that you're able to do your calculations much faster using the new code we've set up compared to what was available previously. Okay, what about the accuracy of the calculations? So we've posted during this project, we've posted this new code onto the GitHub repository. There's a link there, and you can compare the calculations we've done with the calculations of the previous best code, and there's a link to that there. And I've chosen some sample values for t where the absolute value of zt is unusually large. And these are quite important because any anomalies in distribution of zeta function zeros, they are expected to lie in close proximity to a large value of zt. Usually zt is only about a number between -10 and 10. It's not very big, but just occasionally it becomes very large indeed and exhibits some very strange behavior. And that is a sort of suggestion that the Riemann hypothesis is close to being violated in and around those areas. So these points like this are sort of considerable theoretical interest. So I've done some calculations. All the tolerance scale I mentioned before was set to the value 0.005. So the user, you can play around with that. If you make that bigger, you get a faster run, slightly less accurate. If you make that smaller, you get a slightly slower run, which is more accurate. But this seems to be a good compromise value. And you can see the values here. So these t values, they're quite difficult to find, but we're starting at 10 to the 28. We go down to 10 to the 32 here. And this is my estimate. This is the previous estimate. And you can see this kind of relative error that you're getting. And crucially, these relative errors are very much smaller than, this is 10 to the -3, and these are sort of 10 to the -6, 10 to the -7. So they're about 1,000 times better than this tolerance scale here. So they're really very good. And I would say that the absolute errors here, they're going to be largest at the large values. So as the values go down to their more normal values between, say, -10 and 10, the absolute values are going to decline. The errors will always tend to be larger associated with the large absolute values you see here. And we did some sort of groundbreaking computations here. So for the runtime on ARCHER2, these range from about 1 hour on 4 nodes for these guys to about 10.5 hours for this one, these couple on 8 nodes. And then I was able to make use of the capability day, the capability week back in September to do these very large computations here. And we got some, after a little bit of jiggery pokery, it didn't all go quite to plan, but I was able to rescue what data we did, and it came up with some nice comparable answers with what's been done previously. So you can have a look at those. Okay, so I'm going to wrap it up. As I mentioned, Hardy's function is of great importance in the theory of the Riemann zeta function. Obviously, its main focus is on the distribution of the primes, but it also has applications to cryptography and random matrix theory. Despite tremendous historical analysis, many of what its suspected properties, proofs of these suspected properties, remain out of reach. Obviously, the Riemann hypothesis is the most important one, but there are others and other properties that are believed to be true, but no one's been able to prove them. So the aim of the project was to obviously develop these new high-performance algorithms, which hopefully can be used in conjunction with analytical work to perhaps move forward ideas towards perhaps proving some of these things. We developed this open source code on the GitHub site. And what have we got? Well, there are a number of algorithms. The algorithm I've described in the main has been this one of operational complexity t to the 1/4. That's based on cubic Gauss sums. There's a similar code that calculates one value of Z. There's a very similar multi-value code that actually computes multi-values of Z, which are in close proximity to one another. So you can compute 15 separate values. And you think, okay, 15 separate values is 15 times this runtime. But actually, it isn't. You can do 15 separate values, and you only had 10% of this runtime to get your 15 values. And I haven't really looked. You could probably increase this maybe to as high as 40, 50. I haven't really had time to look at that, but something to sort of perhaps work on. And then there's also a code based on the m=4 approximation. Now, in theory, this has potential complex or operational complexity of t to the 1/5 compared to t to the 1/4, so much faster. But in practice, it's only about 20 to 40% faster than 1 above, for around about t to being 10 to the 28. There are certain, problems with the recursion scheme that sort of kick in, manifest themselves when m equals 4 and greater, that actually reduce its operational efficiency, and they need to be overcome. And I say futuristically, what you'd really likely to do is to develop an algorithm for any value of m. So we've got something for m equals 3, we've got a sort of halfway house m equals 4, but what you'd like to do is to say, if you're a user, you could choose any value of m. So you could essentially, you've got a library of routines for m equals 3, m equals 4, m equals 100, say, a whole library, and you take your value of t you're interested in, and you choose the value of m depending upon what your computational resources are, whether you use it running it on a supercomputer or just on the desktop or whatever. You would choose the appropriate value of m to give you a result in the time that you specify, whether it's an hour on the supercomputer or a day on your desktop or whatever it is. You could just essentially work out a particular value of m for your given value of t. And that actually would be not only be very important computationally, but it would also be very important theoretically, because it would actually prove something about the zeta zeros. It would say that the zeta zeros, any anomaly, would be extremely rare. Only a tiny proportion of zeta zeros lie off the line. I think at the moment all we know is that 40% of the zeta zeros lie on the line, but if this was true, that would jump to something like 99.99999% of the zeros would lie on the line, and only a tiny fraction would actually lie off the line. But there are, as I say, some very formidable technical hurdles to overcome. So it really is a somewhat futuristic possibility that I've set out there. Okay, there are a number of references here. These are the only ones that I've used to develop this work. In the main, there are literally thousands of papers pertaining to some property of the Hardy function in the literature. The list here is the publications that I've used in the main, but they all contain further references therein. So the classic one is the book by Edwards. So I've got to highlight that if you're interested in this work. That is where you have to start with, and it'll give you a whole history of the topic. Okay, thank you very much for your patience. Does anyone have any questions about this?
So thanks, David. I'm happy to take questions. You're welcome to ask the questions in the chat. I don't know if David can see the chat, but I'll relay them. So if I have a couple of questions, but if you have any questions, then there's the chat box, which you can ask, in which case I'll relay them. If not, you should be able to speak and get the audio going. But I mean, I had a question immediately. I mean, you said that Alan Turing didn't believe the Riemann hypothesis was true. Do you believe it's true? Or...
That's an exceptionally good question. I think back in 1859, Riemann himself said it was probably true. Okay, and I don't think anyone has gone beyond that. So it's probably true. But when you look at things and you look at studies in detail, I don't think you can go any further beyond the idea that it's probably true.
So there aren't any, often there are these conjectures which people assume are true and then go on to prove lots of other stuff. There isn't some house of cards that would implode if the Riemann hypothesis was found to be false, is there?
If it was false, then it would play havoc with the distribution of the prime numbers. So it would seem unlikely that it's false, because the point where it breaks down would be of very considerable interest, and the distribution of prime numbers subsequently would be somewhat out of line compared with what we have analyzed and we see at the moment. But it's still possible. As I say, you have somebody like Turing who believed it was false, and there are people who will be quite very strongly say, yeah, there's no particular reason for it to be true. Everything would still hold together. If it was false, it'd make life perhaps a little bit more difficult. Things wouldn't be quite as neat and tidy, but the real world, the mathematical world, isn't necessarily neat and tidy. But so that would be my answer. But everything would still hold together if the Riemann hypothesis was false. Yeah.
Because you did say very early on that there was a limit, it gave limits on the number of primes less than some value x. I mean, I was going to say the fact we can look for primes, a lot of prime number searches, maybe that would be a way to look whether it's true or false. But then people look very much for large primes. I guess, I don't, if someone has primes very large prime, but you want to know, you would want to know all the primes up to some value, which I guess
you do, yeah. So I mean, people do look for enormously large primes, but what you're looking for is to find, and they devote a huge amount of computational effort to finding a record, a large prime, which is fantastic work. But this concerns all the primes up to that particular very large prime. So you want to know how many of them are lying up to that point, and that's way beyond computational possibilities at the moment. Maybe it's something a quantum computer might be able to do in the future, but at the moment it's sort of completely out of there's no possibility of doing that.
But there must be some value, there must be some known value for which, there must be some value for which all the primes are known up to some number, and then it breaks down. I guess that number is much less than the very largest, which tend to be special primes, don't they, Mersenne primes and things like that.
Yeah, I mean, I think one famous thing to illustrate is if I go back, I don't know, hope you can still see it.
Yes, we can still see the slide.
I'll go back to the first slide. Here it is. What you actually notice about this, that when all the computations that have been done, the value of this is greater than pi x. So this value is greater than pi x for all the computations that have ever been done. So the error here is a negative term. So it has to be, this has to be made smaller to get the agreement. And this is, I don't know quite how far they've gone, but it turns out that we know theoretically that actually these oscillate. So at some point, this value becomes greater than this. And we believe the number that happens is called what's called the skews number, or skews number, and it's believed to be about estimated around 10 to the 324. So you can go up to 10 to the power 324, and this number will exceed this number, and then this will catch up and overtake it. So you can do all the computations and you might think to yourself, oh, I can go up. It must be always true that this is greater than that. But it turns out, no, actually, it's false. And you get to a stage where 10 to the power 324, it swaps over. And then it will actually, these two terms will oscillate. And I think illustrates the complexity of this term. And as I say, this is why you need to start thinking in terms of being able to compute this for very large values of t, because it would be very useful to be able to do calculations of this thing at t equals 10 to the 324 or whatever, which is way, way beyond what's computationally possible at the moment. So yeah, there are some interesting issues that arise from doing analysis on just on this equation.
Okay, that's great. So that's all my questions. If there are no other questions, I don't see anything in chat. Thanks very much for a very interesting talk. I'm glad that you're able to use ARCHER2 for studying something which is in the realms of pure mathematics. And the recording of this webinar will be available on the ARCHER2 website relatively short, well, as soon as Claire gets a chance to process it. So I'd like to thank you very much again, and thanks for everyone for attending, and goodbye for the rest of the day. Thanks very much. And thanks again, David.
Thank you very much for giving me the opportunity. Thank you.